This is video lecture 12, and in this video lecture we are going to go through the Rescorla-Wagner mathematical model of Pavlovian conditioning. So Robert Rescorla and John Wagner are two Pavlovian psychologists, and together they have developed, not surprisingly, the Rescorla-Wagner mathematical model of Pavlovian conditioning. It is a model that predicts the outcome of Pavlovian conditioning preparations. It is capable of handling a variety of different phenomena that we have already discussed to this point. Now, in this lecture, I'm going to limit our discussion and limit the examples to demonstrations of acquisition and extinction, but know also that it can handle other phenomena, for example, overshadowing, blocking, and so forth. So it's really quite elegant in its ability to make predictions about a variety of different conditioning phenomena. And so the equation for the Rescorla-Wagner model is depicted there in the upper left-hand corner of the screen. Delta Vn is equal to K times A minus Vn minus 1. And so let's unpack each of the aspects or each of the elements or variables of this equation. So K is the most important. That determines the rate of conditioning. K is or reflects the salience of the stimuli. Now recall, I've used the term salience in the past. It refers to the strength or noticeability of the stimuli. A loud tone is more salient than a soft tone. A bright light more salient than a dim light. And so we're talking here about the collective noticeability or strength of the stimuli that are used in conditioning. Now the range over which this value can take ranges from 0 to 1. And so that is it. That is the lower and upper bound of K. And so you cannot have saliences of 3.7. That is not feasible within the model. So it has to remain between, or is limited rather, between the range of 0 and 1, and that does just fine. 0 meaning the stimuli are imperceptible. The tone is too soft. The food is too weak. That the animal cannot, or the person cannot detect these things. They are imperceptible, and therefore will have no impact on learning. 1, of course, is the upper bound, and that means that the stimuli are so salient, so noticeable, that they cannot be ignored. So obviously those are extremes, and they are atypical in most conditioning preparations. Usually the range, or the value rather, of K falls somewhere in between. So we have salience, or K. A refers to the asymptote of conditioning. Okay, recall that the asymptote is the upper bound, or the highest attainable value. It's where conditioning levels off and achieves its final conditioning level, if you will. So what determines the asymptote in conditioning? Well, it's determined by the strength of the unconditioned stimulus, and of course then the corresponding unconditioned response. So if we're trying to predict the outcome of conditioning, or predict the outcome of the conditioned response, we have to have a sense for what the unconditioned stimulus is capable of eliciting in and of itself. So for example, if we use a piece of food in the mouth of a dog, and we know that this particular piece of food typically results in 30 drops of saliva. That is the upper bound. That is the most amount of saliva that we can expect from this particular piece of food. And so now we know the upper bound. It is going to be 30. The unconditioned response will be 30, and therefore we also know what the ultimate endpoint is for the conditioned response. There isn't going to be a situation in which the conditioned response exceeds the unconditioned response. So the asymptote of conditioning, right, the asymptote or final destination, if you will, of the conditioned response will be dictated by the ultimate strength of the unconditioned response. It's not going to ever exceed it, and so we need to know where that final point is going to be. So that's where the asymptote, or A in the model, the asymptote is derived from. Vn minus 1 reflects the cumulative strength of conditioning up through the previous trial. So with conditioning, it occurs trial after trial after trial, and with each trial, a little more associative strength is developed. And so therefore, in the model, Vn minus 1 reflects the cumulative strength of conditioning up through the previous trial. So if you are on, for example, trial 7, Vn minus 1, n meaning the trial number, so n minus 1 would be 7 minus 1 or 6. What is the cumulative strength of conditioning that has accumulated from trials 1 through 6? And then, of course, on trial 7, the current trial will add to that accumulated total once it has been completed. So Vn minus 1 is the accumulated strength of conditioning up through the previous trial. In this case, it's referred to as trial n minus 1, with the assumption being that trial n is the current trial. And then lastly, delta Vn. That refers to the change in the strength of conditioning on that particular trial. And so going back to the example from the previous that I used previously, we have delta Vn. So on trial 7, delta Vn reflects how much conditioning, how much change did we get in conditioning on that particular trial, on trial 7. So these are the components of the Rescorla-Wagner model. And I will expect students to understand and be able to describe what each of these mean. Know what salience is. Don't just say that K refers to the salience. What does salience mean? Don't just say that A is the asymptote. What does asymptote or asymptotic levels mean? And so forth. So I will expect students to understand each of these elements within the Rescorla-Wagner model. Now, one interesting thing about the Rescorla-Wagner model, it reflects its assumptions of how conditioning unfolds. It assumes that conditioning is greatest when the element of surprise is the greatest. It assumes that the greatest change in learning, or the greatest change in behavior, are those trials, or occurs on those trials, that are earlier in learning. So for example, an animal, near the forest, and it's learning, that I gave the example in a previous lecture of Bambi, and Bambi learning to fear wolves. Well, in the first trial, when Bambi sees the wolf and sees his mother's fear reaction, right, and that association develops between the CS and the US, between the sight of the wolf and the fear response in the mother. According to the Rescorla-Wagner model, that's going to be the trial, that very first trial is going to have the greatest element of surprise, because Bambi, or in any other learning situation, has no prior experience with this. And so the change in behavior on that trial will be greater than the change in behavior on the second trial, because now on the second trial, Bambi has had some prior experience. It's less surprised by the pairing of the sight of the wolf with the mother's fear reaction. And then on the third trial, the surprise goes down a little bit more. And so with each loss of surprise is accompanied by a reduction in the change in behavior. And this is reflected in the acquisition curve. If you look at any acquisition curve, you'll see that the steepest part of the curve occurs early on, that the greatest change in behavior occurs on trial 1. And then the next greatest change occurs on trial 2, and so forth. And then eventually that draws this negatively accelerated curve, whereby the change gets less and less and less until eventually it levels off and reaches asymptotic levels. And so according to the Rescorla-Wagner model, they argue that what is driving that is the element of surprise. And I guess, if you will, you can kind of think that the greater the surprise, the greater the extent to which it is, stamped in, or the association becomes consolidated. Of course, those are terms that neither Rescorla nor Wagner would use, but I think they are descriptive in terms of understanding what they were alluding to when they discussed the topic of surprise in their model. So let's go through this. Let's go through an example of acquisition and an example of extinction. So there is the mathematical model up in the upper left-hand corner. Delta Vn is equal to K times A minus Vn minus 1. So let's keep this simple, and let's say we're trying to teach a dog to salivate to atone, Pavlov's model. So you've been doing experiments with dogs for a while, and you have a sense for how salient both the piece of food as well as the tone that you're going to be using. And based on your prior experience, you estimate that the cumulative salience of those stimuli is somewhere around 0.3. Certainly not so weak that, they certainly can hear it. It's not so powerful that it approaches 1, but it's not so weak that it's right up against 0. It's definitely noticeable. The dog can certainly hear it. It's not overly loud, but then again, it's not overly soft. And also the food itself is detectable, and certainly is capable of eliciting an unconditioned response. And so you settle on a value of 0.3 for your salience. You also know that this piece of food consistently results in a total amount of saliva of 90 drops. That you've used this amount of food in the past, and it routinely results in 90 drops of saliva. So your asymptote for this learning curve, in which you plot the progression of the conditioned response, you know that it's going to end up at some point at 90. It will never go higher than the unconditioned response. So we know the asymptote now of learning. So with these two values, we can start to fill in the progression of learning based on these two particular numbers. So on trial 1, you sound the tone, you follow it with food, and so forth. And so now the goal, and actually I think this certainly should be stated, one of the reasons for mathematical models is to make predictions about future events, such that once we have an understanding of different stimuli and different asymptotes and so forth, we can use that without actually having to go through the conditioning preparation. We can actually use mathematical models to predict that with this piece of food and in this animal with these stimuli, we would rather predict that the course of learning will look like this. And so that's the real utility of mathematical models. And then it also allows you to kind of work backward to determine which factors or which variables are the most important operating in Pavlovian conditioning. So on trial 1, you would make the following prediction. Trial 1, delta V1, right, the change in conditioning on trial 1, is equal to the salience, in this case 0.3, times the asymptote, in this case 90, minus 0. Why is 0 inserted there? Well, it's 90 minus, or the asymptote minus the conditioning up through the previous trial. The cumulative conditioning up through the previous trial. Well, there is no previous trial. It's trial 1. So the value of the cumulative strength of conditioning up to the previous trial is 0. 90 minus 0 is 90. 90 times 0.3 is 27. On trial 1, given the value of 0.3, a salience of 0.3 and an asymptote of 90, we would expect a change in conditioning on that trial of 27 associative units, or 27 drops of saliva. Okay, so that's the first trial. Let's go on to the second one. On trial 2, delta V2, the change in conditioning on trial 2 is equal to salience, which is 0.3, times 90, which is the asymptote, minus 27. So why is 27 inserted there? Well, we're on trial 2. The cumulative strength of conditioning up through the previous trial, well, there is only one previous trial, and it resulted in an associative value or associative strength of 27. So in this case, we have 90, the asymptote, minus the cumulative strength of conditioning up to the previous trial, equal to 27. 90 minus 27 is 63. 63 times 0.3 gives us something around 19. Now, I've rounded these numbers to the nearest whole number. You can use decimal places if you wish, or you can round. I have chosen to round up. So now we have a change in strength on trial 2 of 19 associative units. We're already seeing this element of surprise that Rescorla and Wagner wrote about being borne out in our example. On trial 1, where surprise would be greatest, we have a change in conditioning of 27 associative units. On trial 2, where the element of surprise would be slightly less, we see a change in 19 associative units. But we go on. Trial 3, delta V3, or the change in conditioning on trial 3, is equal to the salience of 0.3 times the asymptote of 90 minus 46. Again, 46 represents the cumulative strength of conditioning up through the previous trial. We have two previous trials, one yielding 27 associative units and another yielding 19 associative units. Taken collectively, that's 46 associative units. 90 minus 46 is 44. 44 times 0.3 yields 13 associative units on this particular trial. And again, I have rounded to the nearest whole number. Moving on to trial 4. The change in conditioning on trial 4 is equal to 0.3 salience times the asymptote of 90 minus the cumulative strength up through the previous trial of 27 plus 19 plus 13. That gives us 59. 90 minus 59 is 31. 31 times 0.3 is equal to 9. A change in 9 associative units on this particular trial. And then lastly, we'll carry this out to the 5th trial, but if you were to actually model this, you would carry it out until the condition response neared the asymptote of 90. But for our purposes, we'll just carry this through the first 5 trials. So on trial 5, we have delta V5 is equal to the salience of 0.3 times the asymptote of 90 minus 68. That's the cumulative strength of the previous 4 trials. 90 minus 68 is 22. 22 times 0.3 is 7. And so we have now calculated the projected changes in conditioning for a Pavlovian experiment that utilizes stimuli that are projected to have a salience of about 0.3 and an asymptote of learning to be around 90. Again, looking at the numbers, we can see that this element of surprise that Rescorla and Wagner wrote about is being borne out in our example. As we increase the trial number, the actual change in conditioning is going down. So now, what I would like students to be aware of is to actually turn these numbers into an acquisition curve. It's one thing to say that it's changing, and the change in conditioning is decreasing as a function of trial number, but it's another thing to actually plot an acquisition curve. And so let's do that here. And so here is the projected acquisition curve for the numbers that we just generated. On trial 1, we see, or on trial 0 rather, prior to conditioning, well, the associative strength is 0. So our starting point here is the origin of this graph. It is at 0. But after the first trial, we get a change in associative learning of 27 units. And so now, as of trial 1, if we were to stop right then and there, we would have increased the associative strength of that particular learning situation by 27 associative units. But we didn't stop there. We went on to trials 2 through 5, and so let's plot those as well. On trial 2, we had a change in learning of 19, but the acquisition curve plots the accumulation of learning throughout all of the trials. So 27 plus 19 is 46. So by trial 2, we've accumulated 46 associative units. By trial 3, we've added an additional 13, and so now we're up to 59 associative units. By trial 4, we've added 9 more, so now we're up to 68 associative units. And with the 5th trial, we add 7 more, and so we are now up to 75 associative units. Now, of course, we haven't yet met our asymptote, and if you were to be performing these calculations to make predictions, you would continue to run these calculations until you approached 90. But for our purposes, stopping after the 5th trial is sufficient enough, rather, to demonstrate how this model unfolds and how you can use it to make predictions about various Pavlovian phenomena. So this is a demonstration of acquisition, right? The acquiring of a conditioned response. What about extinction? Can the Rescorla-Wagner model effectively and accurately predict the outcome of extinction? Well, let's go through an example. and demonstrate how it can effectively make that prediction. So the equation is the same. Delta Vn is equal to the salience of k times the asymptote a minus Vn minus 1. And so we need to adjust our numbers a little bit. Well, we're using the same stimuli. Recall, of course, that extinction is the presentation of the CS in the absence of the US. And so what we're doing is presenting the CS to the dog in this case, the tone, and but it's not followed by food. And so how quickly, what will the shape of that extinction curve look like as the condition response begins to diminish? So we're using the same stimulus, the CS here, and so we have the same salience of 0.3. But what changes, of course, is the asymptote. What is the eventual goal of conditioning in a situation of extinction? Well, it's to be back to baseline, or it's back to the goal rather is to be back to 0. And so we need to adjust our asymptote, right? For acquisition, the asymptote was 90 in our previous example. Well, for extinction, the ultimate goal then, or the end point, will be 0. And so you'll start from 90 and you'll end up at 0. So we need to adjust the asymptote to reflect the ultimate goal or end point of conditioning. And that, of course, is 0. And so on the first trial, we have a dog that has already undergone acquisition and is now salivating quite vigorously to the sound of a tone. And so we reflect that in our model on trial 1. Trial 1, delta V1, change in conditioning on trial 1 is equal to the salience of 0.3 times 0 minus 90. Well, 0 reflects the asymptote, and in the cases of extinction, the asymptote is 0. But why is that minus 90? Well, of course, extinction is only meaningful after acquisition. And so to perform calculations, Rescorla-Wagner model calculations for extinction, you have to assume that the response has already been acquired to full strength. And so in our previous example, full strength, was assumed rather to be 90 drops of saliva. So that is our starting point for this example. So 0 being the asymptote, the eventual endpoint of conditioning, and minus 90 reflects the accumulated strength of conditioning up through the previous trial. Well, the first trial of extinction follows after all of the previous trials of acquisition, and so that's where that's where 90 comes from. So delta V1 is equal to 0.3 times 0 minus 90. 0 minus 90 is negative 90. Negative 90 times 0.3 is equal to minus or negative 27. So we are losing 27 associative units, or 27 drops of saliva, after one extinction trial. We move on. Trial 2, delta V2, or the change in conditioning on this second extinction trial, is equal to the salience of 0.3 times 0, the asymptote, minus 63. Well, where did that come from? Well, we started with 90, but we lost 27 units after the first trial. So 90 minus 27 is 63. 0 minus 63 is negative 63 times 0.3. That's negative 19. So we lost an additional 19 associative units on trial 2. Moving on to trial 3, delta V3 is equal to the salience of 0.3 times 0 minus 44. 44 represents the cumulative strength up through the previous trial. That is 90 minus 27 minus 19, and of course that results in the cumulative strength of 44. 0 minus 44 is negative 44 times 0.3, and that gives us minus 13. We have lost on trial 3 an additional 13 associative units. On trial 4, delta V4 is equal to 0.3 times 0 minus 31. Again, the cumulative strength of conditioning. We started with 90, we lost 27, then an additional 19, a further 13, and that results in the cumulative strength up to the previous trial of 31. 0 minus 31 is negative 31 times 0.3, and that gives us a change in conditioning on this trial of minus 9. We lose 9 more associative units. And then finishing off, delta V5 is equal to 0.3 times 0 minus 22. That comes, of course, from 27, a loss of 27, a loss of 19, a loss of 13, and a loss of 9. Those sum to give us 22 total associative units. So 0 minus 22, that's negative 22 times 0.3, and that's minus 7. So we lose an additional 7 units. Now again, take a look at the change of conditioning as it occurs at each trial. Trial 1, we lost 27 associative units. On trial 2, we lost 19 associative units. On trial 3, we lost 13 associative units. And so the change in conditioning is becoming less on every trial. Again, the element of surprise is operating to make predictions about what's happening in conditioning. So we began with 90, but with each trial we lost 27, then we lost an additional 19, and an additional 13, so forth. And eventually you would carry this out until you bottomed out at 0, but we will stop at trial 5 because I think it serves our purpose well, and we can see how this model can be used to make predictions about extinction. So let's then take the next step and plot the extinction curve. What does it look like? Well, extinction then is the situation in which the CS is paired in the absence of the US, and what you get is a gradual reduction in the condition response. Well, we started at 90 units, right? And so here we are on trial 1. We start with 90, but after a single extinction trial, we lose 27 associative units, and so that takes us down to a cumulative associative strength of 63. On that trial, we lose an additional 19 associative units, and so that brings us down to a cumulative associative strength of 44. On the third trial, we lose an additional 13 units, and so that brings us down to 31. And then we lose an additional 9 units, rather, on trial 4, and that takes us down to 22. And if you were to carry this out, this would eventually go down to 0. And that would be assuming that you had chosen your values correctly in terms of the salience of the stimuli. This would be a fairly accurate reflection of how extinction would play itself out, if you will, in a conditioning preparation. Okay, so I'm going to stop there. This was a brief overview of the Rescorla-Wagner model. I will expect students to be able to perform these calculations, either acquisition or extinction, using numbers of my choosing. And so I will give you, if I provide you with an example, I will give you the salience. Assume a salience of 0.4 and assume an asymptote of 120 or whatever. I will pick numbers, and you will have to take those numbers that I have given you and plug them into the Rescorla-Wagner model. I will give you also the equation. You don't have to remember the equation. So I will give that to you to assist in your calculations. But I will expect you to be able to plug those numbers into the equation and make accurate predictions about it, either based on acquisition or on extinction. Furthermore, I will expect you to understand what each element in the equation means. What does K represent, and what does that mean? Don't just say it refers to salience. Indicate that it's salience, and that salience reflects the overall strength of the stimuli. This is also covered in the textbook, and the authors go through a series of examples demonstrating acquisition and extinction. And so perhaps if you are so motivated, maybe you could provide an example of your own and post it onto the discussion threads for some practice, as well as an opportunity to give your classmates further instruction on how to perform these calculations.